Okay, so we'll move on in a second, but just to elaborate on some of the discussions that has just been occurring about hardware counters. This command man hardware program counters, performance counters, sorry, on ARCHER2 can be useful because it tells you what hardware counters are there and what they, what's available and what they should be doing a little bit. Now this documentation is a little bit out of date. It probably needs some updating from Cray, but most of it is there. You'll see there's this PAPI, it itself is using PAPI under the hood, so you can use PAPI native avail and PAPI avail, which should give you an output of what counters are available as well. I mean, this AP run stuff that they talk about here is no longer how they launched things. That used to be their launch command on their Cray job launcher command, but now they use the Slurm one, they use srun, so that's gone. You should be able to use that along with the PAPI counters to get something out of here. And see, if you type PAPI avail, you can see these are all the PAPI counters there are, and then there's a flag as to where we have available ones here. And as has been posted in the chat, if you do a -a, it will tell you the ones that are available, and then you can see which ones are native and which ones are derived. So derived is pre-calculated from other counters, but that's should give you a reasonable introduction to the counters that are available. The prefetch ones that you see in there are probably calculated by CrayPat itself, because you can see there's no particular prefetch calculations going on. Prefetch counters that are listed here, but you probably they can calculate these from some of the misses versus load statistics. So there'll be some load misses and load statistics and miss statistics where you can see you can sort of work out what was prefetched instead. Let's go back to the chat. No, we could ask the Cray team we have here if we can get information on those from the CrayPat developers. So if you're interested in how those are calculated, I can go and ask the Cray team here and we can get some feedback. It'll take a few days, no doubt, but we can go and ask. If you're interested in that, just drop me an email and I can follow up out of band on that. Okay. Any other questions about the profiling side of it? So now what we're meant to look at is optimizing with a compiler. Is the next lecture. That lecture scheduled to run until 3. We might slightly overrun that. And then after that, there is a practical we do, which is actually derived from some of our MSc teaching work. But a practical we can do where we give you a code which is not very good. On purpose, it's been poorly implemented so that its performance is not brilliant, and you can play around with profiling it and then trying to optimize it to improve performance. That's a sort of infinitely long practical. You can just keep going forever and ever on that. So you can do as much or as little as you want. You can just take it, run it through different compiler flags and see what performance you get, or take it and try and do some actual hands-on optimization yourself. There is C and Fortran versions of it, so you can choose your favorite of those two languages and just see how you get on. At the same time, if you'd rather from 3:30 till 5:30, you can do the same thing for your own application. So you can get the profiler out, get your own application on there, run through it with CrayPat, run through it with some of the other stuff, and just see what you get. And if you've got any questions about that, I'm more than happy to talk through those as well. So the afternoon after this lecture is pretty unstructured. As I said at the introduction, no lectures after about 3 o'clock. If you want to hang around and do the practical and talk to me and Mark if he's around, and that's great. If you want to go off and do it in your own time and then come back with questions out of band, then that's perfectly fine as well. So I'll not hold you to be here beyond this lecture, but the practical is quite fun. So if you want to have a play around with it and you have questions, then please do. And then I will get on with the next lecture. And as before, if anybody's still struggling to get onto Archer or doesn't have their account and has thereby not been able to do any practical sessions yet, but that's fine, just let me know. You know, there's plenty of time still to do all the practicals from the day after this lecture. So if you want to have a play around and you've not quite done so yet, then do just let me know. As I say, these things are much easier to teach face to face when I can walk around people and chat with them and see what's going on the screens. As you're all remote, it's a bit more disconnected, which makes it harder for us to track how well people are doing and if everybody's having problems. So do just let me know, or Mark know if you're having problems. Okay, so we're looking at optimizing with the compiler. So I've discussed already today, and we've had some interesting discussions already today about some of the hardware features that your program needs to be able to engage with efficiently to be able to get good performance. And that's what we're trying to do with performance optimization. We're trying to match our program to the hardware it's running on. If you move to a different system, there'll be different hardware and there'll be different balances of equations of what you want to do there. But alongside that, there is always a resource constraint. So you're trying to optimize this application as well as possible on the hardware you have, but you only have a fixed amount of time to do that, a fixed amount of your life to spend on this task. And so we have this idea of, you know, the minimal effort is best if possible. So actually, for a lot of applications people they don't need to do any optimization at all. It runs quick enough for them. It could run quicker, but it runs quick enough for them, and they don't need to spend any more time optimizing it. Obviously, in high performance computing, because we end up running very large applications on very large systems, it's quite expensive, both in terms of time, but in terms of resources, to have applications which are not as efficient as sensibly possible. So there's more of a focus on optimizing them and getting the best use out of their resources. If you're running on a 500,000 cores for a few days and you can go make that go 10% faster, that's quite a big saving. But we have this stronger focus here. But we still recognize the fact that people's time is finite, effort is finite, and so you want to be able to do as much optimization as possible with as little effort as possible, really. And this is where the compiler comes in. So a compiler is our main tool to integrate our application with the hardware, unless, of course, you write directly in assembler code or machine instructions, which happens occasionally, but is not scalable or sensible for large applications. Then you're going to have to use the compiler to take your code and turn it into something that runs on the system. And that means the compiler is our first port of call for optimization, because it can do a lot of work in making our program faster without us even having to touch it, without us even having to invest that effort into programming, optimizing our actual application. Now, compilers are not magic, even though computer scientists would love to think they are magic, and there's plenty of time being spent on projects writing magic compilers, which auto-parallelize your code and will fix everything in the world. But in reality, compilers aren't magic. They can only do so much. So that's where code modification comes in. And that's where there are some things, because the compiler has two jobs it has to do for you. It has 3 jobs it has to do for you, and some of them are key and some of them are optional. The compiler has to take your code and turn it into something that will run, as long as your code is correct. And that's the first job. And during that job, it's going to want to make sure that the code is correct, as specified by the programming language standard and any mapping onto a system there is. So its real focus is correctness, doing something that will, the compiler itself can guarantee will produce sensible results for the instructions that have been programmed in. Obviously, the compiler is not actually looking at your program output, what you're doing with all these instructions, but it's trying to ensure that if you've put A equals B plus C, then A does equal B plus C, and not A equals B plus C and a little bit more, or something else. So what we're trying to do, the other thing the compiler will also try and do for you is make efficient code. But it's still only ever going to make efficient code with respect to the first thing it's tried to do, which is make that code correct. So a compiler will always be constrained by assumptions it has to make about the correctness of code and the operations that it implements, so that the code can be guaranteed to be correct from its perspective. And that can restrict some of the optimizations it can do for various codes, depending on how they've been implemented. And that's where code optimization, hand optimization comes in, where you can go along and say, okay, the compiler is generating good code, but we can see that it's not optimal. You know, if it was optimal, it'd be getting better performance out of a memory system or better performance out of this bit or that bit. But the first part of call should be the compiler. The compiler should be giving us, doing most of the optimization work for us, if we are good and we use it in the correct way. So the reason that it's useful to use a compiler, as I've already said, is it saves human effort. There's only a limited amount of effort you have, but it also saves you optimizing things too far for a specific architecture, which breaks portability. And the compiler can easily apply some optimizations automatically, which you as a human might find hard to do without creating mistakes or bugs. So that's why it's useful to use a compiler as much as possible in your journey on optimizing your code. And then once you've exhausted the compiler, you can move on beyond that. Compilers have optimization functionality built into them, but generally you have to control that as a user, all right? Because there's this balance between correctness and optimization, particularly for floating point arithmetic, the compiler won't always have all the optimization turned on all the time. And depending on what compiler you use, some compilers by default will have no optimization turned on, and other compilers will have some or a lot of optimization turned on. One of the reasons that the Cray compiler is the first choice on a system like Archer is that it has a fair amount of optimization turned on by default. So it should give you better performance by default than, say, GCC or G-Fortran or G++, because they don't have optimization turned on by default. You may ask, why do compilers not just turn all the optimization on by default and not try and produce fast code all the time? Well, there's a number of reasons. Part of the reasons I've already discussed is there's a trade-off between correctness and performance. So there's some optimizations which will change the output of your code depending on how it's implemented. Floating point particularly, because some of the ordering of floating point instructions will change the output. And you know, some of the heavy compiler optimizations, things like imprecise divisions or imprecise modular operations, may be perfectly acceptable for your code, but maybe not acceptable for other people's codes. The other reason that compilers don't have optimization turned on by default a lot of the time is because it's expensive to do at the compilation phase. So it takes computational resources, and it can take up space or capacity or or these kind of consumables for when you're compiling. So if you're building a big code and you're wanting to, you're in that build, debug cycle, you don't necessarily want the compiler to take a long time optimizing the code. You want the compiler to finish quickly, generate an executable, you can test it and see if it's correct. And then later at some point you'll have optimization on, but not during the build cycle. So that's where we are. If you've used high performance computing or computing in general at all, you'll probably be familiar with compiler flags, but they generally have these overarching groups of optimizations which they structure into optimization levels. Level 0, level 1, level 2, level 3, possibly level 4. And these are groups of compiler flags which turn on or turn off different bits of compiler functionality. Actually, you don't need to use these groups with O1 or O2. There's plenty of, you could just take all the raw flags and run them yourself, but it gets pretty tedious to do that. So the groups tend to be quite sensible to use. And the O of a number after the optimization level is meant to describe how high the optimization level has been set. So effectively, it means what optimizations you turn on. The higher your optimization level, the higher the optimizations are turning on. This does not necessarily mean that optimization level 3 will give you a faster executable than optimization level 2. It just means optimization level 3 will have switched on more potential optimization approach in the compiler than optimization level 2. There is nothing deterministic about these things. They're a group of functions or heuristics or transforms to your code the compiler will apply, which generally provide performance benefits for applications, but there's no guarantee they will for all applications in all configurations. So you can quite often see codes where optimization level 4 is slower than optimization level 3, for instance, or optimization level 3 breaks a code, but optimization level 2 doesn't. Okay. But it's important, once we're happy our code is correct, that we use the compiler to get the best performance we can without having to modify our code. And so that generally is a bit of an experimental cycle where we try different levels of optimization with different test cases and check that our results are correct or within a certain tolerance, and then we stick with the optimization level which gives us the best performance with the minimal correctness impact on our code. Compiler documentation is there to help you. So it's excessively long, but buried within that documentation will be some discussion of optimization levels and the optimization flags and what you can use for various compilers. And in case you're not familiar with how you would look at these, I mean, you can search them on the web, obviously. You can also, generally on a system, you can also use the manual pages, the man pages, so to look at the compiler documentation. So I've typed man GCC, and this is the GNU project C and C++ compiler. And then if you go through here, there's lots of discussion, but there's all the different flags that it implements, from warning options to these are the ones that we're interested in for the performance optimization, but you can see there's lots of optimization flags that are available, which is why these optimization levels 0, 1, 2, 3, S, fast, these kind of things are useful, because it saves you having to pick out individual flags here and stick them on yourself. And then you can also look in a bit more detail about what each one of those may turn on. So you can see here we go optimization flag level 3, optimize yet more. O3 turns on all optimization specified O2 and also turns on F inline functions, F's unswitch loops, predictive common in GCSE after reload, tree loop vectorize, tree loop distribute patterns, all these kind of things. So you can get some information about what's going on. And you can see here, minus optimization level 0, reduce compilation time and make debugging produce the expected results. This is the default. So for the GNU compiler, the default is optimization level 0, which will probably not give you fast. It can be for large codes that, and I've seen this happen actually, you test the whole thing with optimization level 2, it works. You test the whole thing with optimization level 3, it's a fair bit faster, but it gives you the wrong results. What do you do in that scenario? Well, you may just go, well, we have to run at optimization level 2 and see what we can do manually. The other thing you can do is this sort of idea of a binary chop, where actually we could change the optimization level for individual files that we compile and see which one is causing the problem. And so I've seen codes where the majority of the code is compiled at 03, but some individual files are compiled at 02 and then all put together. And that gets around some of the problems while still giving, in general, better performance than down at the 02 level. Compiler optimizations are often designed for instruction set architectures, so things like x86, not particularly for one machine. So you can get better performance by targeting a particular piece of hardware as well. So you can say, if you this on the this was on GNU compilers, there's a command like march equals Zen2, I think, for these processors, or march equals Skylake for an Intel processor. If you're on the Intel compilers, it'd be like something like -x host. So you can specify to the compiler, compile this executable for this particular piece of hardware, this particular processor. And it can do a bit more optimization there. It knows things like vector lengths, cache sizes, those kind of things. For a lot of systems, this is done for you by default, either in the setup of the compilers or because the hardware you're compiling on the login nodes is the same as the hardware in the compute nodes. And that's true for ARCHER2. The processors which are we use in our compute nodes are the same as processors that we specify or that we use on our login nodes. So you compile on the login nodes, then you should get an executable that runs on the compute nodes. That's not always true for all systems. Like our previous system before ARCHER2, Archer, it had different processes on the login nodes when it did on the compute nodes. So you had to make sure you were compiling for the correct output. And you know, same being true, if you try and copy an application from another system onto Archer and don't recompile it, you would run into the same problems. Yeah, I see there's a couple of other suggestions for architecture tuning flags. march equals native, and native would be compile, I think, on this processor. So that would work on ARCHER2, but if you're on a system where you're compiling on one processor but running on a different kind of processor, the march native wouldn't necessarily give you the best option. And then there's also yes, an mtune option as well. I'm actually not 100% sure what the difference between march and mtune is. So march is specifying the architecture you're building for, but I don't know what the mtune does on top of that. I'll have to look that up. But yes, definitely I've seen march and mtune give better performance on various systems. On ARCHER2, it shouldn't be an issue. It should all be as optimal as possible from that perspective. Okay. Any other questions? And as it says in the last bit here, some optimization flags may not be part of ON. Yeah, so like O2 or 3, there's some optimization flags which may be switched on in none of those groupings, but you may want to add separately. And an example from the Intel compiler was this thing called streaming stores, which is never turned on by default, but can be beneficial for some applications. Basically, it means that when you write data, you bypass the cache, so you don't ever root your cache with writes, and you can turn it on manually yourself. Oh, thanks, that's a useful note, Bjorn. And so there's examples of those you could look at as well. There are also, as well as compiler flags, mechanisms for ways to give the compiler extra information to help it optimize your code and to help it make sure your code's correct, but in this context, to help it optimize your code. So these are often called compiler pragmas or directives. So in C, pragmas, in Fortran, directives. And it can let you tell the compiler things like, in C, these pointers are not going to point to the same place. So there's no aliasing between them. You can say these loop iterations are independent, even if you can't see that when you do your analysis. This variable is a loop counter. These kind of things can help the compiler do some of the optimization if it can't automatically calculate some of those things. The nice thing about these is there's also ones for prefetching as well. Actually, you can specify prefetching and some vectorization, more vectorization stuff through them. The nice things about these is you're changing your code, but they appear as comments in the code, so they don't affect portability. So if you put them in and then use a different compiler that didn't understand them, it would just ignore them, but they can be useful. Compilers only, yes, so compilers in generally only work as they can only work with the data they have, which makes sense. So they're not generally getting a view of your whole program. They just compile files separately, individual files separately. And of course, if you've got a function or a subroutine in a file, which depends on global variables or has data arguments that are passed in or passes data out, the compiler only has a limited amount of information which you can specify, which you can optimize on top of that. The same with library function calls or other function calls and kind of routines. And so the compiler has to assume the worst for correctness. It has to assume, okay, all these arguments that are being passed in could actually in C point to the same, because they're pointers, they could all point to the same array, so I can't assume they're independent. Or I can't assume that this function doesn't have we don't have any escapes or jumps or anything like that. And that's where we can help the compiler as well with these pragmas or with language features to specify things which let the compiler have more understanding of what's going on. So in Fortran, we can provide information on subroutine parameters, intents and pures and things like that, where we can say this parameter is only passed in, it's not going to be passed back out again, it's not modified inside the function of a subroutine. This is only generated inside a subroutine, so you don't have to pre-populate it, those kind of things. And so we can specify some of those either at the compiler, as compiler hints, as pragmas, as part of a language itself. Things in C like volatile keyword or the restrict keyword do some of this kind of stuff. Things like intent and pure and const in C++. Yeah, intent and pure are Fortran. So it's the way it's written. It's not how you use it. So in Fortran, you would have something like intent in variable. I'm being stupid here, but integer, something like that, where you say, and this is A is a parameter to a function, an argument to a function, a subroutine. And that just says A is passed in, but you don't have to worry about the value that's calculated inside, because it does. I don't want to pass it out again, and then that can let the compiler do a bit more optimization. Pure is a function keyword for Fortran, which says this function does not change any of its input parameters. It produces a result, but it does not change any of its input parameters. Okay, sorry, just getting back to my screen. Then, so we want the compiler to do all the optimization possible for me, but if it fails, then we have to go in and modify the code. Then we have to go in and modify the code and try and change it in such a way that the compiler can then produce optimized code, which can then run fast. Of course, we have to be aware that there is always a cost for changing, optimizing code. We may introduce bugs. We may make the code harder to read, harder to understand, harder to maintain. And we may also end up doing optimizations that only work on certain architectures if we're doing very specific things for the process that we're running on. So they all have to be borne in mind when we do the code modifications, because we damage our code to optimize it. We can damage our code to optimize it. So we need to make sure we're happy to do that. And if possible, what's best is to try and look, okay, where's the compiler failing to optimize this? Why is it not producing this code? Can I rewrite it or add some hints or add some guidance to the compiler or change slightly the setup so that it no longer fails and I'm still getting the compiler to optimize it? I haven't changed my code that much, but I'm getting better performance. How do we do this? How do we work out what's going on with the compiler, whether it's working well or not? Well, of course, there's profiling, which tells us how fast our code is. And then nowadays, compilers have pretty good diagnostic information. So compiler reports. The compiler generally will produce you a report saying, here are all the optimizations I did, here are all the optimizations I tried, but I couldn't do, here are the things that have failed, those kind of things. And then you can go back and look at the code and say, okay, why couldn't it vectorize here? What's it telling me? There's a dependency, it thinks. Is there a real dependency? If not, can I tell it there's not a dependency? What's it worried about this over here? So you can also look at assembly code, and that can work for very small bits of code. But I can't say that I'm an expert at using assembly. I very rarely would look at the assembly. It can be useful to check kind of instructions that are being generated, but it needs a fair bit of time and effort to be invested in it to make good use of the assembly code. But it's easy to get the compiler to generate assembly code if you want. Generally, the -S flag will get the compiler to produce the assembly code it would generate for a particular file. So if you're interested, you can just add a flag in and get the compiler to generate the assembly code rather than an object file. Having said all that, it's increasingly hard to easily diagnose what's going on with your application, because there's a real interaction between your code, the compiler, and then the runtime environment, particularly because we have multi-core with various levels of shared cache. We have out of order execution, superscalar instruction issue, and speculative execution. So we generally, we have to use a profiling to work out how efficient bits of the code are, to looking at flops, load stores, cache misses, and compare that with what you'd expect for that bit of code. How many floating point operations are there in that loop? How many bits of data do they need? Now, of course, this is quite involved work, because you've got to go up to a reasonable level. You can't do it for very large routines, but there are things that can help you. So there are things like vTune, Intel's vTune, which will automatically do a roofline analysis of an application for you, and so that calculates some of these things. Again, it's really more designed for serial applications than large-scale parallel ones, but you can work with some of those tools to do that kind of stuff. Okay, so what are the kind of things that we could change in our code that would help the compiler produce more optimized codes? There are various things, so local and global variables. So compilers, when they're looking through the source code, can make many more assumptions about local variables than they can about global or module level variables. Because the compiler has to assume there may be other threads of this program running. If it's a global variable, other threads may be able to change it whilst I'm using it and all those kind of things. Whereas if it's a local variable or something passed in through the arguments of a function or subroutine, it can make safer assumptions about it. So using local variables where possible, automatic variables and file scope variables, if you're going to go global, is preferable to externals or fully global variables. So conditionals or branches are hard for modern hardware and compilers to optimize. Branching, because of this pipeline issue we talked about this morning, where if a pipeline has to drain down, that's expensive. Branching is hard, is often a hard thing to get good performance on. So there is a branch every time we have an if statement, because it's got to say, is n equal to 0? If it is, execute these set of instructions, otherwise execute those ones. There's actually a branch at the end of this do loop as well every time we go down, but it's saying, is I equal to k or not? Okay, go around. But that's a much more predictable branch. And so the branch predictor can do a good job there, especially if k is large. So we don't worry too much about that one. But sort of if statements inside loops can be pretty expensive. Now, you may not be able to get rid of this. It may just be part of your program. But in this example here, you can see n doesn't change inside this loop. So actually, I've got no reason to have n inside this loop. This may be my most compact, most sensible bit of code I've written. But actually, if I duplicate the loop and pull n outside the loop, this if statement outside the loop, then I only have to do this if statement once, and then the loop can run quite nicely. Of course, this is a pretty simple example, but that's the kind of idea you can do there. So to try and move the conditionals. Now, compilers can do a little bit of this for you, but they've struggled to move them a long way, or to reason about moving them, moving some of them out of the loops. Radim is asking, is it really worth it to use many local variables everywhere? It depends what you mean by use it. Certainly, it's useful to avoid global variables where you don't need them, right? So if you don't need a global variable, then don't use it as a global variable. You can define it inside the main program. If you can define it inside the functions, then that's fine. And if you can pass everything around as function parameters, function arguments, then that will help the compiler. If you're in Fortran world, then of course the real thing to do is to use what we call modules and put our variables into modules. And you could think of as a module as a global variable, but actually when you compile a Fortran routine, you include the modules in every routine that uses it. And so then the compiler has much better view of those variables and where they're created and those kind of things. So it can help the compiler do that. If you in C++ or C, you can get away with header files and having some variables in there, and it may not be as expensive as external global variable. So as long as you include those header files in the correct place, at least the compiler can see what's going on. But the compiler will still have to make some assumptions about that global variable being used elsewhere. But it doesn't have to make about a variable that's been passed in as an argument to a function. Does that answer your question, Radim?
Well, what I meant was, for example, in C++, if we pass some, let's say, complex classes or structures or vectors of these structures as a parameter to some function, doesn't make sense to then copy the actual values from these structures into some local variables? Or is it fine to just
No, absolutely
read
not.
directly from these references? because
use them directly from those references.
yeah, because I think that copying them to the local ones would be like excessive usage of.
Yeah, absolutely. Absolutely. So in this context, local means things that are contained within the routine. And in that sense, the function parameters can be considered local as well. So it's really global variables that appear in the routine but are not actually passed in as parameters we're talking about.
Maybe I have a comment and a follow-up question. Like I can testify that really using local variables is a good idea in some cases because we observed in our codes when we were using a global array. So basically, a C compiler treated these accesses to these global arrays as basically volatile. So even though we reuse these values quite often in subsequent code, uh, the basically the load and stores instructions were there, and when we switched to a local array, basically compiler will able to keep these values in registers rather than doing really load and store operations on these values. So that I observed this firsthand. So it really has an impact. And then the question is there, for example, we have a quite a lot of, not quite a lot of, but quite a large amount of data. For example, some 9 by 9 matrices, and to actually allocate a local array, it's quite inconvenient, or maybe even like local variables. It would be just too tedious to define it. Is there some way around it, or like any other trick to tell the compiler to treat, even though it's like global variable, global array, to treat it like a local one?
Yes, it is possible. So there are things you can do. It depends what language we're talking here. Are we talking C or C++ or Fortran or something else?
C and C++.
Yeah. Okay. So you can have things as global variables, or more easily as pass them in as parameters to the function, if you could do that. But tell it that it's a restricted thing, so nothing else will be using it whilst it's in there. And then it should be able to treat it as if it was a local variable, even though it's not a local variable. So that
Okay.
should be possible. I'm not sure if it's possible. I'd have to look up, I'd have to remind myself of the C++ standards. If it's possible to do it as a truly global variable, but still reuse it locally, there may be a keyword you can use for that.
Yeah.
You know, you
I'm
can
sorry.
do the sort of pointer thing as well. If it was a truly global variable, you could alias a pointer inside the routine, restrict that pointer, and then use it locally, and it should, as long as no one else is using that pointer as that external memory, as long as you're sure that's safe, it should be fine.
Yes, it's in a scenario where every thread it's working on its part of the memory, so there is no
Overlap.
overlap, and that it doesn't change under the hand of the thread. So it should
So
be
then, yes, there are tricks you can do with restricted pointers or something like that, which should still give you the optimization. The compiler can still happily say, okay, I'm happy that that's a
okay.
local
So
variable.
something like a local pointer with
Yeah,
restrict keyword in
yeah,
front of it. Mm-hmm.
yeah.
Okay,
It should.
have to try it out. Yeah, thanks.
No, thanks for the feedback as well. Any other questions?
Does it also apply to references? Not the pointers, but references in C++?
So the references in C++ are there to be much more restricted from a compiler point of view. So the compiler is much happier about optimizing around references than it is around raw pointers. So it shouldn't apply as much in C++ references.
Okay, thanks.
Mark's also commenting that compilers can be very poor at storing array elements in registers. I guess, Mark, it also depends on how well they vectorize, because they should vectorize, yeah, temporary scalars kind of. They should, if you can vectorize as well, then the array elements should go into vector registers. But when we're starting to get into the complexities of multi-optimization. Thanks, Mark. Yeah, so this example here is easy for us to see and should be easy for compiler to see. N doesn't change inside this loop, so we can hoist the conditionals outside the loop and put the loops inside the conditionals, and it should produce the right source. And the compiler may be able to do this for us. We can start to look at things, you know, where it's harder for a compiler to do that reasoning, but the same thing still applies. Actually, we've got a conditional inside the loop. The conditional is changing as a loop going on, but the condition that it's compared against is fixed. So J is fixed inside the loop. And so we can actually create two different loops, one from 1 to J and one from J plus 1 up to K. And we can get rid of that conditional altogether. Now, you see here that I think the code on the left-hand side, I guess most of you are not Fortran programmers, so it's maybe not that understandable. But the code on the left-hand side is probably more understandable from what the developer of the application wanted to do, which is to say, do this whole loop, but for part of a loop, do this, and then for part of a loop, do that. And then we've moved it into a slightly different form, which has got two separate loops. And now it may be as understandable, but you have to watch when you do these kind of transforms that you don't lose the understandability and in the sort of descriptiveness of the code. Or if you do this optimization, you put plenty of comments in to say, look, what I've done here is I really wanted this bit of code, but it was slow because the compiler wasn't recognizing it, so we've transformed in this. And that way you help your future self remember what you did here and why you did it. We can also help performance, not particularly the compiler here, but just performance in general, by looking at data types. So there's a flip side of this coin, actually, which we'll come on to, but we can look at data types to reduce the cost of things by saying, well, actually, I don't need 64-bit floating point numbers or 64-bit floating point numbers here. I could get away with 32-bit floating point numbers. And if we can do that, then we can halve the amount of memory we need because we can fit more data into our storage. We're only using up 32 bits per element of our array or whatever it is. That means we should get more benefit of a cache reuse as well, because every cache line has now got twice as much work in it. We can also potentially vectorize more because our vector units can do, say, 4 double precision floating point numbers at once, but 8 single precision floating point numbers. So we can get performance benefits by not changing the application, but by just changing the data types it uses. If we use a smaller data type, we can get better performance up to a point, right? So traditionally, floating point and integer units could do single precision, which is 32-bit, and 64-bit double precision. And so you had a choice there. We've seen a much bigger move recently to smaller precisions, so 16-bit, 8-bit, and this is often driven by machine learning tasks, which can get away with low precision for some of their operations. And so there is a more of a range of precisions you can choose for things. And of course, the smaller precision you use, the less space you use, and potentially the higher performance you get in terms of vectorization, the more data elements you can operate on at once. Of course, you can only use what you can use. So if for your application you need 64 bits for accuracy, then you need to use 64 bits. The reason we mention it is that quite often people just assume they need double precision floating point numbers when they've never tested and never really looked at what precision they actually need in their simulations or their code. And so there may be a chance to switch to 32-bit stuff or some mixed precision bits where some parts of your code use 64-bit and some parts of your code use 32-bit. It needs some work. It needs some analysis. You need to have a look at what your tolerances are for precision, but that can be beneficial. I've also seen applications where the opposite is true, of course, where everything's been done in 64-bit, but actually if you run it for long enough, you need 128-bit. So you have to be careful that you're not doing optimizations which impact the correctness of your code over time or for larger test cases. We see the same thing where you scale up a CFD application on a large mesh, and it suddenly gets to a point where it needs 64-bit integers to index the mesh or something like that. And so then for a functional point of view, it's not a performance thing, but you have to switch to 64-bit indexing from a functional point of view, and that of course can also impact performance, but you have to do it. So just be a bit careful around there. But there are some big wins that can be achieved if you can get away with reducing your precision and still get correct results. Moving between data types will cost you. You've got to avoid sort of unnecessarily ints to longs, floats to doubles, those kind of things, unless you need them. And so, for instance, you could have a reduction variable where you're summing up to get a final result from an array, and you may want that reduction variable to be in double position and still have your whole array in single position. So you may need to mix the types as you go through the application. Then there's a whole bunch of things that hopefully you shouldn't have to do in your application, but your compiler will be doing for you. And these are things like a CSE, common sub-expression elimination. And so that's where they go through and say, okay, you're recalculating these things. You don't need to. We could just reuse this variable we already have, which you've already calculated of these kind of things. This will often go off, the compiler will often be able to pick this up for you, but there are a few places where it's not necessarily easy for a compiler to do that. One may be, and the compilers get better over time at these kind of things, so some of this may no longer be as much of a problem as it was before, but sometimes when there's different orders of operands, so here we've got D equals A plus C and then E equals A plus B plus C, and obviously E could just be B plus D, but the compiler may not be able to see that because you've got, it doesn't recognize the pattern of A plus C. It's doing, you've got to remember that compilers aren't that clever, can't be that clever. They're doing simple pattern recognition, pattern substitution, these kind of things. And so if you don't match a pattern it already has, then it's just going to ignore that optimization that it could do for you. Of course, you could just then go into your code and remove this sub-expression anyway, or you could reorder it so the compiler could automatically remove it. Compiler also struggles to do this common sub-expression removal when you've got functions involved in it here, because it can't guarantee that function running on C is not going to change next time you run it. But you yourself may know that func C doesn't change every time you run it unless C changes. So you could store that into a temporary variable and then reuse it rather than calling the function each time, because a function call is quite an expensive thing to do unless it's been inlined. Yes, the compiler will try and do these if you've got a function call there, but the function prototypes have to be quite good so the compiler knows what's going on inside that function call. As we've already seen this morning in the hardware, there's a fixed set of registers that the local storage the processor can use, and so the compiler tries to do this job of maximizing the use of registers so that it can have as many instructions in flight as possible. But we have a limited number of registers, right? So there may become times where the code the compiler is generated and the code the CPU can dispatch just runs out of register space. And so it can't run a new instruction until those registers have been freed up, until some of those instructions have run through the pipeline, data's been taken out, stored into memory somewhere, down the cache or something like that. And so that's what we call register pressure. And so this can also slow down, and it doesn't come up as a cache miss. It doesn't come up as one of those kind of things, but we just end up retiring or issuing less instructions than theoretically we should be able to on this processor. So we have an instruction stall, and we can see that sometimes. Depends what compiler, what processor counters we have, what hardware counters we have, but we should be able to see some of those coming through in the metrics. When does this happen? Well, large loops with large numbers of temporary variables, large loops that have got lots of going on in them, array elements with complex indexing expressions, so indirect addressing, and those kind of things. And is there any hardware counters for? So often there are hardware counters for instructions issued and instructions retired. The question, of course, is what do we have on ARCHER2? There are instructions completed is one of the hardware counters, and there's also floating point instructions and total cycles. So I think from instructions completed and total cycles, you can probably generate a synthetic metric which pulls up some of this stuff. You may want to take into account the other things. So yeah, in fact you'd have to take into account the other counters that are going on there, so cache misses and those kind of things. It's a shame because there are other processors which give you direct access to instructions issued and instructions completed or retired, which we don't get the same from the current AMD EPYCs that we have, but maybe in other ones. Well, okay, so how do you, if we calculate the IPC, how do you identify as an issue with registers? It's hard to do that without doing some looking at the actual assembly code and program you've got in front of you. No, so it can be a compile time problem, but then because we do out of order instruction issues, then it can be a runtime problem as well, the register thing. So we can have this hit us in both places, both at the compile time thing and at the runtime thing. So this is part of what Mark was talking about earlier, where compilers sometimes won't use a register for array variables, and so you can force it to use registers if it's not using registers, or vice versa. So yeah, it's not easy to identify some of these issues, but sometimes looking at the assembler will let you see what's going on. There could be more loads from L1 cache, or there could be more memory operations as opposed to register loads in your assembly code that you can see for this bit of part of the code which is not going as quickly as you would like. So yeah, an example here is calculate the temp. So instead of doing this indirect addressing here, where the value of A's index is looked up from C, which is quite common in old scientific codes, because this is what often you had to do for getting good performance on vector systems in the past. You had to have sort of strided array access or indirect addressing, and actually it didn't cost you anything, but nowadays it tends to. But if you can get this C outside the loop and just have a temporary variable, then you can get rid of some of that pressure there. You're not needing, so you can assign a single register for this. You're not having to reuse registers and these kind of things, and we can go around the loop. And yeah, so if a compiler runs out of registers of it will generate spill code. So this is code to temporarily take some of the data, store it, and then read it, load it later on. And so we can have a look at the assembly code for that and examine the source code and count how many load stores there should be and how many are actually happening from the assemblers, from the performance counters we had. And in that case, it may be that you need to split up some complex loops into what we call distribute loops, into loops which are a little bit simpler going forward. The compilers may give you warnings about spilling if you look at the compiler optimization reports. It depends on the compiler we're using and what optimization report levels you got turned on, but they can often give you warnings that's happening. Yeah. And again, this is a reason why it's sensible to target, necessary to target your compilation for a particular hardware architecture, because then it'll know exactly how many registers it has access to. It can't use it. It doesn't have to use a defensive assumption on that. Loop unrolling can be useful for in generating reuse of data and sensible cache use and filling up our pipelines. You can imagine that a loop like this one here, where actually you can see that the number of operations we have to do to run the loop, so a branch at the end, the increment of variable I, the comparison of a variable I, these kind of things. If we add more work inside that loop, we get more work to the overhead of doing the loop itself. This is what we call loop unrolling. In general, the compiler will do this stuff for you. Okay, so you don't have to go and damage your code by taking this and then turning it into something like this. If it doesn't do that, if it can't unroll the loop sensibly, and that may not be, it may be because it thinks there's dependencies between loop iterations, which is one of the same blockers we get when we try and look at vectorization and improving vectorization from a compiler. Then if we can go into the code and alter it so that the compiler can unroll for us, that's the best thing we can do. If we can't get the compiler to agree that it will auto unroll it, then we can go in and do it by hand. We can do it ourselves. And this is where we unroll the loop manually. So we turn this loop here on the left-hand side into this loop here on the right-hand side. We unrolled it by a factor of 4. But we have to do the logic ourselves to handle n being any size. So here we've got to say, is n, we've got to make n less than a certain amount, go up by increments of 4, and then handle any leftover variables, any leftover amounts there are. And you can see this is a much cleaner loop on the left-hand side. This is much nastier to have in your code. And of course, this is now a little unportable as well, right? So on a different system, the optimal unroll factor may be different, and you'd have to go through and change these 4s everywhere. Whereas if a compiler can do that, or at least if we can factor it out into a single, pre-compile time variable, then we can get around that. So the unrolling is a commonly used compiler technique to improve performance, but sometimes you may have to do a little bit of it by hand, and I've seen it before in other codes where they've got good performance by manually unrolling the loops themselves. The compiler, has this problem. It generally can't unroll too far because we run out of registers again, so it doesn't want to make the loops too big. And if it's complex control for those kind of things inside the loop, it'll run into problems doing that. So you may have to help it with those kind of things. Now, of course, applications often have nested loops, so they're not just a single loop. And then we have the compiler will generally try and unroll part of it, but generally it'll try and unroll the innermost loop. It's also possible to unroll the outer loop as well to get you better performance in various scenarios. And that can help you improve locality. So in this case here, and we've not really discussed this here yet, but the memory, the way, if we have multidimensional arrays, the way they're stored in memory is important to us in terms of performance. A multi-dimensional array in C or Fortran in a language like this is really just a group of single-dimensional arrays stuck together. So there'll be a dimension of the array which is contiguous in memory, which means it's one long block of memory. And then when that's loaded up in cache and cache lines and things, we gain we gain spatial locality in that group. And then as you go through the other dimension of array, you're stepping over each one of these contiguous array elements. And so what you want to do for performance is make sure your contiguous dimension is the one that you're iterating over the quickest in a loop nest. Now, in Fortran, our contiguous dimension is always the leftmost one. So for Fortran, which this is, this array A here, all the elements of I, of this first dimension, will be stored consecutively in memory. So from 1 to n, it will be one long block of memory. And then for j, that steps over consecutive blocks of memory. So that moves, every time we move j, we move by n elements. Okay. Now you can imagine if we're going to go through this and we're going to load up cache lines, if we go through this and I is the quickest loop in the middle, well, then we'll load up a cache line, we'll go through all the elements of that cache line, we'll load up the next cache line, we'll go through all the elements. Whereas in this form we have here, where j is the innermost loop, actually we'll load up a cache line for I of 1, and then we'll move on and we'll load up another cache line for I of 1 and j of 2 and I of 1 and j of 3. So that loads lots of loads from main memory, and we're not reusing any of that data until we've gone all the way around the j loop and come back around. And by that time, our cache data may have been evicted and we lose that locality. Now, of course, the sensible fix to do here is just to swap the loops around. So the j becomes the outer loop and the I becomes the inner loop. But the other thing you can do is you can unroll the outer loop, the I loop. And so in here we've got I, we're not changing j, we're making I unrolled in here. And that means that we'll use the first 4 elements of the cache line of A that we've loaded up each time around this loop. And that can give us better performance. This is a much bigger performance pattern than just unrolling. So if you have this loop ordering issue, array ordering issue, then you really need to fix it if you're not accessing memory in the most optimal way, if you can, for your program logic. The nasty thing is that in Fortran, it's this first entry which is contiguous. If this was a C array, it's the last entry, it's the last dimension which is contiguous. So C and Fortran are opposite on these things. And then there's all sorts of other clever things that the compiler will do, but these aren't things that you should do manually generally. But the compiler will do things like expand variables to try and break dependencies between loops. So this is sort of doing a reduction variable by odds, so that it can unroll this loop by 2 because it's now got a B1 and a B2, and it's not dependent on the value of B each time around the loop, which would stop it unrolling it because of a dependency on B, and you can't do each iteration of the loop separately. So, and this is a very common form if you do OpenMP and OpenMP style reduction optimization. The compiler will do this for you. The compiler will also do things like register renaming, so that it can reuse data and hold data back, so that it can be used for other parts of the application, and software pipelining, so that it can make sure that dependencies between instructions are scheduled outside their workflows, so that they don't stall each other. And so they can be compiler will be doing quite complex things under the hood to be able to mix these load and addition and store phases, so that it can build a pipeline which can run without dependencies, rather than one where each time round we're dependent on waiting for some result to be calculated before we store it, and that leaving gaps in our pipeline. But this is just an example of the kind of things the compilers are doing under the hood. It's not stuff that we should be worrying too much about. But when we start, if we started to look at assembler code and what the compiler's doing, we should be able to see some of these kind of things. So where are the situations where you may have to go in and fix things for unrolling? So function calls inside the loops make it hard for the loop to be unrolled. Conditionals, so branches or go-tos or computed go-tos can be bad. And pointer array aliasing. And the interesting thing is these are very similar to the same issues you see for vectorization, automatic vectorization by compilers as well. Basically, there are things which say, I can't tell if these loop iterations are independent, so you need to help me make sure they are, because I'm not going to do this optimization, be it rolling or vectorization, without you doing that. And so here's an example in C, where the compiler doesn't know that this A of IP and this A of index I here don't overlap in some way, because index of I could be the same as IP, and if they are, then it's harder for it to unroll. And so then it's possible for you to do things like pull out one of those parts into a temporary variable, and so now temp doesn't change inside this loop, so the compiler can reason about that more sensibly. Or we can use a pragma to say there are pragmas which say this loop is independent, and so you can ignore the fact you may think there's a dependency, or you can say that index is a permutation, and there's hints we can pass into the compiler there. And then compilers often are restricted in the kind of optimizations they can do because they are working on individual functions or individual files. And if they could see the whole program, then there are more optimizations they can do. So one of the ways we can do this is what's called inlining. This is taking small functions, and instead of using them as functions, manually, compiler will take that code and put it in the place it's being called from. This is inlining, and this lets us get rid of the overhead of the function call, get rid of the overheads associated with the siloing of that function where the compiler can't see the optimization options across that. And lets it be done in such a way where you don't have to manually do this in your code, because that would cause lots of code and lots of code replication where you've got the same code repeated in many places. So it breaks the nice function subroutine logic in that way. And so inlining is one of those nice things that the compiler can do. Not always, and it will have limits on how big a routine it will inline, and so you can alter those limits. You can say inline things up to 100 bytes, 200 bytes, those kind of things. And it will also have limits on what it can see of a program, so it may not be able to see the functions it needs to inline, and so you may have to enable what's called interprocedural optimization, where the compiler will try and save state from other things it's compiled and reuse that in later compilations. And this becomes quite a useful optimization flag, but it's quite intensive for the compiler to do, so it can be a tricky one to compile big codes with. Okay, so what do we have for the compilers? I appreciate we're running on a bit here, apologies, but as I say, after this, you're free to play with codes, do profiling, and ask questions, and you won't hear from me too much again. So we're nearly done. The Cray compiler has a whole bunch of optimization flags, as do all, but we can have a look at things like -02, which I think is the default one for the Cray compiler, -2, -03, and then -0 IPA, so that's inlining, so you can control the inlining level. You can use this -h list equals A, and this is for C++, this is for Fortran, -RA for Fortran or RM. That will produce your optimization reports from the compiler to say why it's doing things or why it hasn't optimized stuff. And then there's parallelization stuff, so there's OpenMP functionality, threaded parallelism, those kind of stuff. So the default optimization level is good. There are ones on the Cray compilers you can go to a higher level, so -03, -HFP3, which is a floating point model 3, and gives you less safe but faster floating point optimizations. But yes, these are all configurable, and you should play around them and test them for correctness as well. So you can have the optimization level and manually change the floating point optimization level as you're going along. OpenMP is on by default for the Cray compiler, but you may want to be able to turn it on and off, and you can do that. There are also auto-threading functionality with the Cray compilers. Although I've not tried that for a long time, so I don't know how valid that still is now, since Cray compiler, C compiler at least, moved to the Clang stack. We also have the GNU compilers and the AMD compilers. The AMD compilers are quite similar to the Cray ones in a lot of ways, because they're now based on the same underlying compiler, at least at the C and C++ level, not so on the Fortran level. But the GNU compilers are great, but their default performance level is conservative, and so you probably want to manually turn on performance optimization for those kind of compilers and play around with that. There's a whole bunch as well, so if you want that detail, you can come back and have a look at it. But these are just different compiler flags which do different things for either Fortran or C. And that's the end of that. Now, again, that's a lot of detail to give you. And you could do a whole course, a whole MSc on a whole degree on compilers, really. But really, the message is the compiler is the first port of call for our optimization. Make sure we're using sensible and the best we can optimization levels to get best performance. Have a look at why the compiler is not giving you good performance for various routines using the compiler reports. Then you can start going in with directives or code modifications to help with that and move it in that way. And then if you get to a point where you need to do something more manual, then that's perfectly fine. But starting off with a compiler will give us the best benefits for the least amount of effort generally, and help us save the quality of our code going forwards. Any questions? Okay, so if there's no questions at this point, where we can take a break, you can definitely take a break. Sorry, I switched myself off. We can take a break now. Then for the rest of the afternoon, what we're back to is, let me check what I'm doing. We're going back to the practical notes. And there's a compiler optimization exercise, which is a separate handout again. And that's to play a little bit with compiler optimization. And then there's a general optimization handout, which is the code that I mentioned earlier, which is a exercise 4 of the optimization, which has been specifically designed to be poor performance, and you can play around with it with the compiler and then look in compiler reports and play around by hand to see if you can improve the performance of it, the C and Fortran versions of that. Or if you want, take your own application, do the same process on that. So profile, look at the compiler flags, then look at seeing which bits of our code we would need to modify to improve performance. Any questions? I'll bring those up on the screen anyway, just so, no, not that one. I don't want to do that one. So yeah, exercise 3, compiler optimization. It has its own handout, which is this one here. And this is looking at, various things we can do: cache optimization, loop and rolling, and basic optimization. So have a play around with that. And then exercise 4 is the molecular dynamics code, which is poorly written. Can you go and have a look at using the compiler and profiling to get the better performance? And if you want to, you can move on to do hand optimizations if there's bits that make sense to you there. And if you want to play on your own codes, then please do that. And give us a shout. As I say, that's where we'll sort of finish at this point. Let you get on with work, but I'll be around here till 5:30. So any questions along the way, any problems, just give us a shout. And then tomorrow, Mark will pick up the baton and talk about OpenMP stuff and vectorization and memory stuff. As I said, Mark, if you want to switch around the lectures, I don't know if you're around still, but if you want to switch around the lectures, then you can do. The timetables there for changing, but at the moment it's OpenMP first and then vectorization stuff and memory stuff after that. And I'll give you that reminder again, but not for now. There's the feedback page for the course on the ARCHER2 website. It's very useful for us to get the feedback and let us know what you thought of the course, what could be improved, and those kind of things.